All right, go ahead.
My apologies. I thought I had started this presentation and I didn't. Anyhow, welcome and greetings to everyone. This is yet another in a series of technical talks from the Networking Storage Forum of SNIA. This one, entitled Revving Up Storage for Automotive, deals with storage in the automobile space. Of course. Those today on this call include myself. I'm Tom Friend. We have the experts in the field being Ryan Suzuki from Samsung and John Kim from NVIDIA. Now, before we get too far into this, I'll give you a couple tips that'll make this easier for you. First is take your browser to full screen, and that will allow you to better see the small print and fine details that appear in some of our slides. If you wish to have a set of those slides for yourself, the Attachments tab in your browser will give you access to that. And we ask that you stay long enough on the end to give us a rating so that we know how well we've done on this. We will gladly take your questions, and sometimes we'll answer them on the fly. Other times we'll answer them at the end. And if we run out of time, which would be a bad thing to do, then we will answer those in our blog. So we will do a follow-up in our blog space, answering any and all questions that appeared in this. So SNIA, the Storage Networking Industry Association. Who are we? We're 180 leading organizations in the storage industry. Companies that manufacture, that test, that use, that provide, that have everything to do with storage in the computer industry. There's over 2,500 active contributing members to this, and we serve over 50,000 IT end users and storage professionals around the world. Topics that are of interest to us include storage. Everything's about storage. You can read through all of this. And it's not only the protocols and the networks that connect these storage devices, but things like security. How do we deal with the security issues around this as well? Of course, this wouldn't be a proper thing unless we actually did all the legal stuff. So everything in this presentation is copyrighted by SNIA unless you see otherwise on an individual slide. Member companies and individuals are free to use this material in presentations, but we have a couple provisos. Any slides you use must be used in their entirety without any modification, and we wish to receive credit for this. This presentation is a product of SNIA. None of us presenters are attorneys. We don't play one on TV. Nothing in this presentation is intended to be or should be construed as legal advice or an opinion of counsel. If you need legal advice, please contact your attorney. The information presented herein contains opinions of the authors, organizers, and those who are active in putting this together. The current understanding of the relevant issues involved is what we're telling you. The author, presenter, and SNIA do not assume any responsibility or liability for damages arising out of any reliance on or use of this information. No warranties, express or implied. Use at your own risk. Okay, and now on with the show. Our agenda for today, we begin with talking about automotive storage trends. Then we'll cover special requirements for autonomous vehicles. Where is this data stored? Some of the special and interesting use cases, and the networking and compute challenges that go along with using storage in the automotive space. So, whoops, I drank too much coffee. I twitched too fast here. Okay, so we'll begin with Ryan, but take it away, Ryan Suzuki.
Thanks, Tom. My name is Ryan Suzuki, so I'm Product Marketing Manager for Automotive Memory at Samsung. Today I'm going to start off talking about, just kind of the general, what we see with regard to storage in the automotive. And I'm primarily focused initially on in-vehicle market numbers. So we see a couple of applications which are really driving the growth of storage within the automotive space. And first one's the in-vehicle infotainment, or what we call IVI. And that's really just like kind of that center screen, which is in your dashboard, right? And it's evolved significantly over the last few years from kind of a small 6-inch screen, which held maybe displayed your radio information and maybe your GPS map information as you're driving, to really kind of now being the center hub of the vehicle, right? Seeing screens as large as upwards of 13 inches in size now. And we're seeing a lot more functionality coming into it. So we're starting to see now streaming coming into it, both music, video, as well as even gaming. So these systems have evolved quite a bit, and we're even seeing some even GPUs, which are now being required in order to drive the graphics involved in there. And of course, that is now also driving up the storage requirements in order to store the information and as well as the applications that are coming in. Second one is advanced driver assistance systems, or ADAS. And that's basically kind of any type of safety related applications for the vehicle, right? To avoid accidents. So I think about it like your lane keeping, or your automatic braking, or even your adaptive cruise control. And then of course, autonomous driving, which is the next step. So those are all those functions, but the addition of the fact that it doesn't require any human intervention anymore, right? The car can actually make all the decisions on its own with regard to, how to avoid accidents as well as to maintain driving. Second one is, and then the last one is the connected car. Now, this isn't in and of itself a massive driver, but it's enabling the previous ones that we talked about. So, the connected car is any type of wireless connection. So that's, it could be Wi-Fi, it could be 4G, 5G, or even Bluetooth. And what that's enabling is it's really enabling kind of the software upgrades of the vehicles, right? Within the operation, anytime during the life of the vehicle. And that can be security updates, additional features or new features which are coming in, as well as any type of potential bug fixes for the vehicle. All right, on the next one. So from a kind of just a high level look at the market. So first, starting with just the total number of vehicles are manufactured worldwide. No surprise, obviously, the last in 2020 was a massive drop off due to COVID. And in 2021, we're seeing kind of a jump up recovery of it. Recovery probably isn't going to be quite as large as what we're showing here. We don't have our latest updates, but we think it'll probably be south of the 80 million vehicles this year. But the thing that I wanted to show is, despite volatility in any given year, we see that on average, the vehicle growth rate is going to be about 4% moving on out through the decade. That's fairly healthy for the automotive market, but it's not really what I would call explosive growth in any way, shape, or form. But if we take a look now towards the right on the storage per vehicle, we see that it's roughly about 40 gigabytes today, and will be, grow more than 10x that by the end of the decade. So the key applications that are driving that, if we come down here from a revenue standpoint, if you see that it's really your IVI and your ADAS, which we talked about on the previous slide. Growth-wise, we're looking at roughly about $1 billion currently, growing to more than about almost $7.5 billion by the end of the decade. So to kind of take that snapshot and go a different way, if we take a look at the interface of the storage market that we see today, we see it primarily kind of three different interfaces. Today, the main one is embedded memory, or eMMC, which is our embedded multimedia card. It's just basically a different form factor, but it's effectively the same spec as what the cards we used to use for our DSLRs to store the images. And that's primarily kind of driven from the mobile phone market kind of into the automotive space. But what we're seeing today is actually that it's starting to migrate towards UFS, or universal flash storage. That's currently also primarily used in the mobile phone space. But the advantage of UFS is that it actually has a higher bandwidth, or IO, as well as higher capacities versus the MMC. So that's kind of the trend moving towards the UFS. And then for the high end, from a performance as well as capacity standpoint, we'll see SSD starting to kind of really start picking up in middle of 2025, or middle of the decade. From a density and interface application, now, if we take a look at those interfaces and kind of lay them out across kind of a table of your density versus your IO bandwidth, we kind of see the applications and where they're being used. And obviously starts on the telematics and the gateway, kind of the lower end, MMC and UFS, as well as ADAS. And then as we go up towards the infotainment, and then finally into the autonomous driving, we start seeing that the performance and as well as densities start increasing quite a bit. One thing that's not on here is what we call our level 5, or that's the fully autonomous vehicle, or robotaxis. You may hear about that. So that's where it's just basically the vehicle just operates on its own, doesn't even require any type of person in there. Even today, those are currently using NVMe drives, and we're seeing that the density trends in those are actually going on even further, probably in multi-terabytes. So just kind of wraps up the overall marketing. And now I will hand it off to John.
Ryan, thank you very much.
Yep.
So as you said, there are these major trends, and they're increasing the amount of storage in each vehicle, as well as the performance requirements of that storage. So I want to talk a little more in depth about some of the trends that you've covered and what's driving that and why vehicles need more storage and faster storage today. So I think the first major change is that modern vehicles run heavily or entirely on software and data and applications. So if we look at, say, a vehicle from the 90s, it had software, it had chips that were controlling engine performance and emissions, and maybe the stereo, but it really didn't have any other visible software or screens other than that. And pretty much it didn't have any other sensors. It really just had things related to braking and engine performance. But now, pretty much all the modern cars have sensors for parking, for optimization of the engine performance. So they're sensing temperature, they're sensing location. If they have batteries, they're tracking the battery performance and charging. And so the entire process of running the engine and the car and optimizing the driving performance is now heavily reliant on software and electronics. And likewise, as you talked about, the user interfaces and the in-vehicle infotainment has become much more sophisticated. There's big improvements to the autonomous and assisted driving. And in fact, the better the autonomous driving gets, or then whether rightly or wrongly, the perhaps greater demand there is from the driver and the passengers for in-vehicle entertainment, since the driver may be doing less and less actual driving as the car is becoming better at doing the driving or doing autonomous driving. And then, of course, there is the tracking and navigation and remote diagnostics, which I'll talk more about in just a minute. There is, as you said, the communications with the car. So there are software updates that have to go with the car. There's tracking, telemetry, and maintenance that goes back to either the car manufacturer or car owner or both. And then there's data transfer for the assisted driving systems, autonomous driving, and I think, as you'll be covering more later, Ryan, covering the perhaps communication between cars or between cars and other edge devices that help manage traffic or accidents or smart city functionality. So all this means there's a lot more storage in the car, and that storage has to get better and run faster. And there's some other storage requirements outside the car as well that I'll talk about going next. So let's move on to the next slide. So one type of storage that's inside the car, that's a special case, is the black box storage. And this is storage that's meant to record what happens during an accident and in the 30 or 60 or 90 seconds leading up to that accident. So typically, the storage wants to record, of course, the speed, but also whether or not the accelerator or brake was being applied, the steering inputs, the G-forces on the car. All modern cars have accelerometers that can be used for stability control and traction or improving the vehicle handling, but also measure exactly which way the car is going, whether it's going forward, backwards, or sideways during an accident or right before the accident. These systems record whether or not airbags deployed. They record video from both from outside the car and possibly from inside the car, video of the driver, and as well as radar, LiDAR, and possibly audio inside. So similar to how all modern planes have a cockpit voice recorder and a black box that tracks all the inputs that were done and the sensor readings right before any crash, modern cars also can do this. And increasingly, I think, may be required to do this, where they're able to store a certain amount of data about what happened right before and during some sort of incident or accident. This data is used to help by the police or insurance companies to help determine the cause or the fault of accidents, of course. So for any possible criminal charges, or for as well as for civil liability and insurance. But it also helps the manufacturers and possibly civil engineers design safer streets and safer cars, better software for the future. So of course, normally, with traffic cameras and accident reporting, you can sort of track which parts of the city have the most accidents. But with this type of data collection, you can also understand what types of conditions or driver behavior or interactions with other cars or other features of the city or the streets might lead to more accidents, and what you can do to improve that and reduce the number of accidents or the severity of accidents. So this storage has some special requirements. It has to record a large burst of data very quickly. It actually has to record the data from before the accident. So that means that usually it's recording some part of data all the time in a continuous loop, and then it freezes that or saves it right when there's an accident. Because you can't have an accident and then say, oh, go back and remember what happened for the 30 seconds before. So what you actually do is you record everything all the time for, let's say, continuous loop of 30, 60, or 90 seconds. And then you actually save it to a durable storage right when the G sensors or the airbag sensor or the accelerometers detect that some sort of accident happened. And ideally, the storage should be able to survive, of course, the impact, possible fire, and it should be tamper resistant so that, say the lawyers or insurance people or the driver aren't able to alter it after the accident before the investigators are able to access it. So that's a special kind of storage that's increasingly present in most or all new vehicles. All right, then there's the general case. As Ryan said, one of the three trends driving it is the ability to collect data from cars or actually communicate with the cars. And this is, so I want to talk specifically about sending data from the cars back to other people or other places that need that data. So first of all, the car manufacturers increasingly are storing telemetry from the cars or information. And this is used for marketing and sales to help determine, for example, when you might want to sell a new car to someone, or when you need to bring them, suggest maintenance or upgrade a car, or when a car is getting old or a lease is about to expire, they can figure out how to best position another vehicle for that customer. It can also be used for predictive maintenance. As something as simple as tracking when a certain mileage has been achieved, or for looking at the behavior of the car and the settings of the engine and the performance of the battery and figuring out if any particular maintenance or upgrades or repairs are needed. This telemetry is also used to improve the software of the car, so you can actually upgrade. Increasingly, as cars use more software, they can have more of their features upgraded while the car is there without having to physically swap out any parts or without having to upgrade to a new model. You can make a lot of improvements to the performance or behavior or interfaces of the car while it's in use, and as well as for planning for future products and better hardware and software in the future. In some cases, the employers of commercial vehicles want to collect data for the job, for job safety, for driver training, for driver performance, for customer interaction. So if you have a delivery vehicle, you want to be able to make sure that deliveries were made on time, that the drivers were driving safely, and that nobody was trying to steal packages from the truck. So video and G-force accelerometers and other telemetry from the vehicles help ensure this. If you have a police car, they're going to be recording anytime they turn on the sirens or anytime they're going to be recording from a dash cam. And increasingly, taxis, rideshare vehicles, buses, and trucks have cameras that are running all the time and recording data for safety and insurance purposes, as well as for possibly training or evaluating the drivers. So what happens is when you have all this data in the car, this data can be uploaded over the air, OTA, continuously through a Wi-Fi or satellite, Or if the data is too much to upload wirelessly or too expensive, you wait till the vehicle comes back to the garage or the home or the charging station at the end of the day. And then you either use a physical wired link or you have high-speed wireless that's available at the garage or the house to upload the key data when the car is docked or charging or parked overnight. And in some special cases, like with police dash cams, they might actually unplug a data canister or a storage module from the trunk and then bring it into the office or data center and upload the data that way if they can't get the data through quickly enough through a wireless connection or a cable brought out to the car. So once you get this, you have this data then becomes off-car storage, and it usually has to be retained and protected. So you usually want very reliable storage that's been replicated. It could be local, it could be in the cloud, but it's quite likely to be object-oriented storage because you're storing a lot of data that you don't want people to be able to change it, or it doesn't need to change. It's often video, it may have audio, it may have photographs or radar tracks of GPS tracks. So this is often used in object storage, and in many cases it goes into the cloud because it's easier to replicate or protect the storage in the cloud than it is out of one facility. Or it could be hybrid. You keep one copy in the data center for the car maker or for the delivery company, and the other copy goes into the cloud for backup and redundancy. And I think Ryan will dive more into it, but in some cases, this drives the need for edge storage, edge compute, or computational storage, because the car could be considered an edge device, as well as the Wi-Fi base stations, or the retail stores, or the truck depots, or the bus station, or the taxi depots, or any place where the vehicles go, police stations. These can all be considered edge locations as well that may need to do some temporary storage or processing of the data, either in real time or upon nightly upload. Okay, let me go on to the next slide. Okay, and then finally, it turns out that the more sophisticated the car, the more advanced the car, the more storage you need to design the car or to train the car. So it turns out that it used to be cars were just made physically built. They're modeled out of clay to get the appearance, and then they would take little tiny models and run them through a wind tunnel to figure out how to improve the aerodynamics. And then they would physically build some prototypes of the cars and then crash them into a wall or crash them into each other in a lab in order to figure out how they perform during crashes and how they could maximize driver safety and passenger safety. Increasingly, this is all done electronically. It's all done in simulated environments with virtual reality or software simulations. In many cases, they may still do a physical test at the end, but they can save a lot of money and a lot of design time by running most of these tests and doing this design simulations in software on network computers before they do it physically with the car. So in the physical design of the software, you have CAD and MCAD, as well as PLM, product lifecycle management. And that's figuring out how the mechanical stresses are going to be there, how to improve strength to weight ratios, how to make the car as light and as strong and safe as possible, as well as having a lot of space on the interior and good visibility out of the car. This can all be simulated and tested electronically in software. And FEA is finite element analysis, which helps you figure out where the forces are going to be directed within the car as you build it or as you design it. And then the chips that go in the car are often designed with EDA or electronic design automation software, and that's done both by the car makers and by the suppliers who supply the vendors like Samsung or Siemens or others who actually supply chips that go into cars. And so that requires a lot of compute power and a lot of storage, as does aerodynamic simulation and then the crash simulation. So CFD is computational fluid dynamics. And that's again simulating, you can see the diagram with the red, green, and yellow. That's showing what does the airflow look like around the car and how can I change the outline or the position of the mirrors or the angle of the windshield to get better fuel efficiency, which is a requirement. New cars are increasingly required to be more fuel efficient than before. For the manufacturing, you have the ability to simulate the factory as well as simulate the service and maintenance of the car. So in a modern car factory may have millions of parts and many assembly lines and doing multiple models. So there are now what we call digital twins, an entire virtual factory designed and run online with the power of artificial intelligence to help you figure out how to make the factory safer and more efficient, and reduce error rates. And so basically these days, any complicated factory gets built virtually and run virtually before it's built in reality. And then the existing factories can then be optimized by, again, using this digital twin process, as well as figuring out how to train. I forgot to say, you can use virtual reality to help sell the car and train the mechanics that work on it. So if you can't get a person into the showroom for an exotic car or a fancy car or a model that's not in stock at the dealer, virtual reality now lets them experience what the car looks like, or pretend to sit in the car, or pretend to drive the car, even if they can't get to the specific model they want to see in person. And that all of these processes require lots of compute power and lots of storage, though that's all storage outside the car. And typically that storage is getting faster. And in many cases, it's shared storage for some of the design processes. All right. And I believe I have one more. Oh, no, actually, at this point, let me hand it back to Ryan to talk more about some of the specifics around the storage requirements in the vehicle. Ryan?
Yeah, thanks, John. So, yeah, I just want to talk a little bit more in depth about autonomous vehicles and some of the requirements, at least that are required for it from a storage standpoint. The first is, what's actually needs to be stored. In case of autonomous vehicles, there's really two different types, right? If you think about it, there's code, which is basically your storage for your inference in your high definition maps. And those will be updated. Now, the maps probably fairly frequently, because there's always constant changes in the roadways. You could have closures or construction going on and so forth. So those need to be constantly updated. And then the inferences, those will constantly always be kind of, I guess, the thought process there is that all the information that the car collects and sends back to the cloud and the data center will then, be used to constantly improve the algorithm. So those will actually need to be updated as well. Also on the other end is the data logging end of it. And this is where the data is actually, this is all the information coming in from the sensors that are then being stored in and then will eventually be sent back to the data center. When we're looking at this one, so I would call this a little bit more complex, because this one really needs to look at what's your performance that you need, and primarily a sustained write. Depending upon the resolution of your sensor suite that you have, obviously you have that information coming in. You need to make sure that all that information is being captured and stored properly. In some cases, what we're seeing is the sensors are constantly actually improving their resolution, which then continues to drive up the actual performance requirements that are there. The second one is also the compression, right? If any is being used. In some cases, some manufacturers don't want to use any type of compression. They want just kind of the raw data, and then to be able to process it at a later date, or a later time, I should say. Next thing to consider is the endurance. How often are you writing to it, right? And then how often are you writing the drive? If you don't do this correctly, you could wear the drive out very, very quickly, or within a short amount of time in operation of the vehicle. Also, the type of vehicle that's being used. Is this just a standard private passenger vehicle, or is this maybe something that's used more, say, like a robotaxi, right? And because of that, the hours of operation per day, as well as the lifetime vehicle operation, are different. And then lastly, the qualification. You have AEC-Q 100 at a minimum, right? And then also now we need to consider the functional safety. So ISO 26262. These are being used in an autonomous driving system, which is, obviously life critical in some cases. So what does that need to be? Then also, do you want to have a single storage unit? Do you want to have different storage units like one for the code, one for the data? So these are all things to consider when we're doing the designing autonomous vehicles, and especially with regard to storage. One thing I wanted to touch on in one area is kind of relatively new, but I know there's been quite a bit of talk about it in other applications, is actually computational storage. And computational storage, what that is, it's where we have processing capability in the SSD, or basically stored right next to the actual memory itself. And And there's a couple applications that are potentially of use within the vehicles. And actually, some of these are actually being prototyped now by some vendors. One is when we talked about all that data that it's collecting, right? In a normal operation, the way it does is you have your sensors, which are recording your data, and it sends it in to the system, and it gets processed probably by an accelerator like a GPU, which then gives that kind of the information to the CPU, which then determines what it needs to do, what the vehicle needs to do at a higher level. That information then is actually taken, or the data is actually taken and stored in a SSD to be transmitted up to the data center at a later time. But in most cases, that data is great, but it actually needs to be processed before it can actually be used in your machine learning, and to actually do the training of the algorithm. Instead, if you think about it, this could actually be quite time consuming when we eventually get to millions of vehicles on the road sending up data every single day to the data center. Instead, what could be used is actually where we actually update the information locally. So in case of, say, an HD map, if there's something that it detects, the vehicle detects as it's going through that isn't on the map, say like a lane closure or construction or some other types of obstacles that it needs to go around, it can actually update its map internally within that vehicle, right? So it gets the benefit of the information immediately, and then eventually that'll also get transmitted out to other vehicles at a later time. In addition, you can also do the labeling, right? Actually, the object recognition and tracking that can actually, it can actually do that on board with the vehicle, and then when it passes it up to the data center, that it actually doesn't need to actually do that pre-processing. You can automatically just use that information and just start doing the training immediately. So a couple different applications. One is to consider, from a storage standpoint, at a special use case, what we could actually be doing more with memory as well. We've talked about kind of the storage within the vehicle and, of course, storage at the data center side. But there's kind of an area in between where there's also another case for storage with regard to automobiles. And that's more on the traffic management side. And there's a couple of use cases where this actually comes into play. And really what we're talking about here is where we have what we call a roadside unit. Those are effectively gateways, right? So it can communicate back up to the data center or to other roadside units, right? And which are located along a road, periodically along a road, or even a highway. However, what we can do then is actually connect a processing power to that, right? So some type of an edge server with storage on it, which can then hold various different types of applications. One case for this would be adaptive traffic control. I mean, I'm sure everybody can relate where they've pulled up to the traffic light during commute hour and they look in both directions and there's nobody moving. All you see is red lights, and the only green lights you see is maybe kind of turnoff lanes, which nobody is in, right? So it's just not very efficient. Instead, what we could do is have cameras monitoring the intersection, feeding it back up to the roadside unit, or then it could actually process that information, determine what is the best, how to optimize the traffic, right? And the traffic lights to keep the traffic going. In addition, this is actually good because during the day, traffic patterns will change. Initially in the morning time, you'll have, commute, and then even in the evening, but maybe going in opposite directions. And during the rest of the day, you can have very, very intermittent kind of traffic. Second use case is sensor extension. So now that we're going to have these vehicles with all the different type of sensors on them, how do we leverage that to be able to communicate to other vehicles if there's, say, an object or a potential issue upcoming? I mean, it could be something in the roadway, or maybe even reduced visibility, let's say like fog is coming in. Well, ideally, it would be for the vehicles to communicate to one another, right? So vehicle-to-vehicle communication. And in that case, the vehicle in the back can then take that information and act accordingly, and then also send that information further back. But in some cases, it'll be a long time, like a number of years, before we actually see the majority of the vehicles on the road actually equipped with this type of equipment or capability. If you think there's roughly 200 million vehicles on the road in the U.S., and on a normal year, we're roughly around 16 or 17 million vehicles sold within the U.S. So from that standpoint, you can kind of do the math. It's roughly going to be quite a number of years before the majority of the vehicles on the road change over and have this capability. An option, though, is that most people do have a mobile phone. So what it could do is if there's gaps within that transmission, is actually to also not only transmit to other vehicles, but to transmit it to an RSU, which can then transmit to other RSUs back down the line of the roadway to give the driver a warning that you need to start slowing down. There's an issue about a quarter mile ahead, say. So. And then finally, I just want to talk about quickly kind of just the networking and compute challenges. So kind of the architecture that we see in vehicles today and where that architecture is kind of going towards or driving towards. So today we have a domain architecture, and that's where the vehicle functions are separated into specific, domains or functions. So there's a specific SoC or ECU for a given function. That could be, say, for ADAS, or infotainment, or powertrain. And all these ECUs are then connected up to a central gateway, which can then pass information as needed to, from one ECU to another to operate. And from a memory standpoint, each of these domains has its own separate storage, right, or some type of storage device for the application. So it could be any of the ones we talked about previously, so eMMC, UFS, or even PCIe or NVMe. But as these technologies have kind of matured, one of the things that we've started to see is that we need to figure out how to kind of actually try to reduce the cost of the vehicle, or the electronics within the vehicle, I should say. Currently, it's roughly about 40% of the vehicle cost is electronics itself, right? And that's actually expected to continue to grow. So in order to get to where we want to from a processing standpoint for autonomous driving and all the other applications that we like to see coming in the future, we need to figure out how to do that kind of cost effectively. And the thought process of doing that is to actually consolidate the domains into more of a centralized platform. And instead, what we'll have is a kind of a zonal architecture where we have zonal gateways, which basically collects all the information from the sensors for all the applications within that given region of the vehicle. So you can, for instance, you could have the front driver side, and basically all that information from that zone would be, anything from the ADAS to the powertrain, whatever information it's getting. You can then do some pre-processing, prioritize which is the most important, and then send it up to the central processing module to consolidate the information from the other gateways and then actually act accordingly. So what this really then means is you have multiple applications running in the CPU. So it's effectively doing a virtualization in a hypervisor style network. So what does this translate to? It means it's higher speed buses that are going to be required. So higher speed PCIe, or even going to higher capacity Ethernet. What does this mean for storage? Well, for storage, as we've seen that we're trying to consolidate the ECUs or the SoCs into the central processing module, we should also see a consolidation of the memory as well. That just means that all the memory and the density, you're going to have one or maybe two storage devices. So that means the densities for those are going to increase, as well as the bandwidth requirement, right? Being able to have to service all these different types of applications. In addition, since you're having different applications, it will need to support a hypervisor or virtualization. So looking more and more, the terminology we've used in the past, or it's been said, is that cars are becoming data center on wheels. That really truly is looking like that direction we're going in for the future. So in summary, automotive storage growing pretty rapidly within the vehicle, growing about 31% annually. It's driven by two main, applications, basically IVI and advanced driver assistance, or ADAS / autonomous driving systems. However, the data collecting to, obviously during the vehicle operation really is driving the growth of off-vehicle storage, in addition to potential other areas of just traffic management. And that's it. Tom, hand it back to you.
Thank you all, especially thanks to Ryan Suzuki and John Kim for this fascinating look into their world. When we're done with this webcast, please give us a rating, give us any feedback that you think we need to know. This is how we improve and make more interesting presentations for you. This webcast and the slides, if you don't pick them up today, you will find them on the SNIA's website in the educational library. And any other questions we'll pick up in our blog. But we do have a number of questions we can go over as we begin. First, I leave this up to whichever. What kind of endurance does automotive storage need, giving the average or 99th percentile lifespan of a modern car?
Ryan, I think that's probably for you.
Yeah, so there's no real, I don't know, that I have a hard number that I could say, and that really does depend on, again, like I said, some of those requirements when I put in there for the autonomous driving, right? It really depends on what's the life of the vehicle and what are your expectations for your data, right? So it is a challenge right now, I think, to be honest, for the manufacturers, right? Because most drives, even still, unless you put in a huge density, you're going to have an issue, right, longer term for the life of the SSD. You might even have to replace it maybe once, maybe even twice, depending upon the amount of usage in the life of a vehicle. So things to consider, and that's, I guess, manufacturer by manufacturer developing the systems, what they're trying to do from a cost standpoint. So sorry, no quick hard number. I wish I could give you.
So in theory, we could end up seeing a normal part of maintenance being the replacement of your brake pads, your air cleaner, and your SSD.
Possibly, yes.
It could happen. Not saying it will. So will 5G networks change how much data vehicles can send and receive while driving?
John, you want to take that one, or?
Yeah, certainly. So 5G allows higher bandwidth. You can send a lot more data, either download or upload, but it also has shorter range, so you have to have more cells and more transmitters. So I think first what we'll see is that as 5G rolls out in major urban centers or places that are heavily connected, you'll have a lot of 5G coverage. But then when you get out to like more suburban or rural areas, you may not have any 5G coverage for a while. The other place you can have 5G coverage is locally. You can have special dedicated 5G coverage, like within or one campus or one building. So that could be really useful for uploading. So that may mean that when the police cars come back to the station or the buses come back to the depot, they can use a local 5G network to upload their data really quickly, wirelessly, but once they park, not while they're driving around, because they may not have reliable 5G coverage everywhere they're going when they're actually on the road. So that said, I think eventually 5G will lead to the ability to upload and download more data. Therefore, you could have more or bigger storage in the cars because you can save more data and then upload it. But as Ryan covered, some use cases require uploading the data or downloading data, and some don't.
Okay, thank you. Ryan, I'm guessing this one will be for you. Does automotive storage need to be ASIL B or D certified?
Yeah, ASIL B or ASIL D. So that's in reference to functional safety. So I think, again, it depends on what it's being used for and what system it's being used in, right? So again, a little bit not quite a straight answer, but so if it's a nondescript, critical system, then it probably doesn't need to be ASIL D certified, right? But again, like I said, I'm trying to understand it myself, where it's going to and where it's going to be moving towards. If we're going more towards, like I said, that centralized system, and there's only one in there, I would expect that, the safety requirements are going to actually have to be increasing on those drives. So going more towards, more towards D, if not D.
Yeah, I think just in general, storage and the electronics in the car have gone from something that's helpful, but if it failed, you can keep driving the car usually, to something that is critical. Now, some of it, if it fails, you may not be able to change any settings, or you may not be able to drive the car at all. Mm-hmm. So
generally there is a backup. I mean, in a critical safety system like, ADAS or advanced, or autonomous driving, where in the worst case, if the main compute fails, there's a backup, so that at least, it won't just stop functioning, right? It at least maybe realize there's an issue and pull off. But yeah, there's generally has to be some type of a backup and some safety, systems involved there.
Mm-hmm. This one, similar question, issues of safety. Now let's talk about security. What prevents hackers from breaching these automotive storage systems and modifying the car's software, deleting critical data, modifying what's in the black box?
So as of now, there's no real, when we've been talking to our manufacturers, they're pretty secretive on what they do. We do know that there's at least an encryption on the data as well as the code, right? It's not just in there for anybody to access. But is there internal, or is there any type of encryption within the SSD itself on top of that? I think, again, it depends on the manufacturer and what they want to do, the individual automotive manufacturer. But I mean, that's definitely a question, and actually, I think that'd be a great topic for another webcast to do. To be honest with you,
what kind of storage media? I mean, not so much media as formats are used. In terms of, is this simple block storage like computers? Is it a file storage, or object based?
I can take that one, or we can both take it. So in terms of the storage media, I guess that wasn't the question. Brian did cover that in one of his slides, but the storage format, I would say it varies quite a bit on the type of data. So if something is more like a database or a track of parameters, which are pretty well understood and aren't changing, it's likely to be some kind of block storage. And I would think most of the storage inside the car is generally likely to be some kind of block storage. For storage outside the car, that depends. If it's for the vehicle design, like you're doing this engineering simulation or stress analysis or aerodynamic analysis, that tends to be high performance shared file storage. So it's usually like a distributed file system or very fast NAS, network attached storage, because you often have multiple machines that want to share the same data and access it really quickly. For storage outside the car, like storing archiving video or audio or driving parameters, or accident telemetry, there's a good chance that's going to be object storage, because it's not supposed to change. It's often long-term storage. It's often big, and it doesn't need the really fast performance, because you're not doing a real-time simulation on it. You're just saving it so you can play it back or analyze it later. So that's more likely to be object storage. Ryan, any comments on that?
No, I think you covered it pretty well.
And in a similar vein about how you store these things, do either of you see a need for redundancy, things like RAID or erasure encoding?
I have not seen the
improving reliability is.
Yeah, I mean, I guess in theory you could, but obviously, again, it's a cost trade-off, right? I mean, I don't know if any data, even if you're trying to store the data, right? Yeah, I mean, to upload later on for inferencing, if that were lost, would that be detrimental? Maybe not. The black box case is a little bit different. And of course, those are designed specifically to record, to make sure they're recording a certain amount of information, right? So I haven't seen any need for a RAID system.
Yeah, I would just comment that outside the vehicle, they tend to use whatever standard either RAID or ratio coding methods they would normally use for the storage, both for the maybe some of the simulation or design storage. If it's short term, they might skip or get away without using RAID because they have data sets that might only be used for 3 or 4 or 8 hours at a time, and then you replace it. So some of that they theoretically could get away with no RAID, but any long-term design data, any archival data, any telemetry you're saving, there's often a regulatory requirement to keep it for a certain number of years. Like some design data, they might have to keep for the life of the vehicle plus 5 years, or plus plus 10 years after the last date of manufacture, that type of thing. So a lot of that would just have standard redundancy, either RAID or erasure coding, and then often replication to a second or third location. But that's for off-vehicle storage.
Sure. Okay. Do you know of any specific storage requirement, design, and whatever, in a car or the back end RSUs, whatever, specifically to meet the UN ECE 155, 156 documents?
So I'm not overly familiar with those. I believe those are related to cybersecurity, right?
I'm not either. This came in on our thing, and that's a new one in my background too.
Yeah, so since that's unfamiliar to me, I'm going to say I have not heard of any of those requirements. That's not to say that people aren't looking into them. I'd be surprised if security is the main concern. I guarantee that it is, but I have not heard of either of those requirements.
Another interesting question. What is the anticipated hourly storage needed? At one point, this was in the multiple terabyte range.
Yeah. So again, this goes back again to we've talked to several different manufacturers, and they're all kind of cagey on giving us kind of that information because it's, I think, kind of their secret sauce, right? What they're doing. But yeah, I mean, I think it ranges, right? It could be from hundreds of megabytes to maybe in the terabyte ranges, right? Of what they're doing. There's not one given number. Again, it depends on, like I said, those factors of the sensor suites, what they're recording, the compression of anything that they're putting into the data into the SSD.
Mm-hmm. Let's see. There was. Here's an interesting one. Does the chip shortage that we're experiencing mean car companies are putting less storage inside new cars than they think they should?
I don't think so, but it's at the margin, if a car company could put in less than they thought was optimal, but they would still put in at least enough to meet all the anticipated needs of operating the car. So let's say for infotainment, they normally said, oh, we're going to put in 2 terabytes to store X number of movies. They might say, oh, well, we'll put in 1 terabyte for movies and store half the number of movies. But for the car operational systems, for ADAS or autonomous driving, for the black box, they can't really change. They've identified what's the minimum requirement. They can't lower that, even for the chip storage. Instead, I think they end up just producing fewer cars or trying to substitute. Maybe they'll go to a different supplier, or they might put in slower or more expensive storage chips if those are available as a second choice. But they can't really reduce the amount of storage inside the car.
Yeah. So yeah, to add to that point, I agree. I have not seen during at least this chip shortage them actually trying to reduce the amount. I think if there's something that's been in production already, right, where they've been having issues, they're not going to reduce that amount during the production. I think there's like John said, there's a minimum amount they've got to support For newer designs, I haven't seen them slowing it down either, right? If anything, it's trying to figure out how to manage what they need, right? But they're, to go to that standpoint of, are they putting in what they need or trying to do minimize? There's always that trying to, cost optimization, right? They would always love to have more margin from any type of, either capacity or any other type of performance standpoint in a design, but there's always the cost aspect that they have to keep in mind.
Okay, well, we need to wrap up. There was a comment that came in on the question explaining that the UNECE spec deals with software updates. So we'll research on this and answer you more accurately in our blog. Give us some time, because we have day jobs, and we will get back to you on this and post the details in our blog, probably within the next week or two. So as I said before, please rate this webcast. Slides are available now and will continue to be available at that link. QA and everything will appear shortly in our blog, shortly as in a week or two. And please follow us on Twitter to find out more information about up and coming broadcasts. And we will answer any and other questions. Thank you so much for everyone attending. Thank you again to Ryan and John for your expert view and a look into the world you live in every day.